Hi there, Mr. Holcomb here with another episode of The Math Behind the Modules. Okay, welcome to Lesson 24, Congruence Criteria for Triangles, Angle Side Angle and Side Side Side. Classwork opening exercise says, use the provided 30-degree angle as one base angle of an isosceles triangle. Use a compass and a straight edge to construct an appropriate isosceles triangle around it. Okay, so here's what I'm going to do first. I'm going to take my ruler and I'm going to put it right there, and I will use a color other than black so we can see my other half. And I'm just going to draw a segment. Length doesn't really matter. So there it is. So I drew a segment. What I'm going to do next is I'm going to put my rule or compass on the vertex of the given 30-degree angle. I'm going to open it up. I'm going to form an arc like so. I'm going to leave my compass at that opening of 30 degrees of that angle. We don't know the measure. I didn't measure it. Actually, it says 65 degrees right there, but it doesn't matter. And I'm going to draw an arc like so. So that's the first thing we do. Then I'm going to take my compass and I'm going to put it right on the intersection of the, come on now. All right, right there. And I'm going to rotate this around. And then I'm going to close it so it's at the desired right there. So you see how I've got it open from intersection of the arc and the ray and the other ray. So it's the width on that arc from the intersection point to this intersection point. I'm just going to draw a little mark right there. Actually, I should maybe open that just a little bit more right there. And I draw an arc. Then I move this over to the end point here. Okay. I'm sorry, to this point right here, the intersection, and I draw an arc. It's off just a little bit, so let me just move that up. Right there is better. Okay, right there. Okay, so let me delete that first one. I was off just a bit. Okay, so there's the duplicates, and then I'm going to put my, I'm going to rotate this around. I'm going to put this right at 0. You don't have to put yours right at 0. I'm just doing that so it rotates on that point. And then I'm going to draw a line segment from here up. And I went beyond like so. So now what I want to do is rotate my straight edge, bring it back over here, and connect these right there. Rotate this like so, and extend this. Okay, so if I look and measure this, this should be the same as the other leg. So this is 63 millimeters. And then if I measure the other leg, it is 63 millimeters. So this side is congruent to that side, which means it is isosceles. Okay, so there's an isosceles triangle with two base angles of 30 degrees. Now down below it says, compare your constructed isosceles triangle with the neighbors. Does using a given angle measure guarantee that all triangles constructed in class have corresponding sides of equal length? Well, the answer to that will be no. And the reason is, if I now take, let me make this all one piece. Maybe it already is. No. Let me choose this segment and this segment and make it all one piece. Now watch, if I drag this out and move it back here, the legs are getting longer, the two congruent legs. So if I continue to intersect, that will still make a triangle as long as I close this in. But now this side is congruent to this side, but they're longer. Or if I move this closer, like so, really close, like that, now this triangle's still isosceles. This side is equal to this side. So they should not have equal lengths of someone else's triangle, because wherever they put the vertex of the second base angle determines the length of the sides. Okay, page 2 brings us to a discussion. Today we're going to examine 2 more triangle congruence criteria: angle, side, angle, and side, side, side. To add to the SAS criteria we have already learned. We begin with the ASA criteria. So it says angle, side, angle, triangle congruence criteria, ASA, states that given 2 triangles, triangle ABC and triangle A prime, B prime, C prime, if the measure of angle CAB equals the measure of angle C prime, A prime, B prime, which is an angle, side AB equals A prime, B prime side, and the measure of angle CBA equals the measure of angle C prime, B prime, A prime, another angle, with an included side, mind you, then the triangles are congruent. The side must be between those 2 angles, by the way. So proof. We do not begin at the very beginning of this proof. Revisit your notes on the SAS proof and recall that there are 3 cases to consider when comparing 2 triangles. In the most general case, when comparing 2 distinct triangles, we translate one vertex to another. Remember the vector translation, moving a vertex to another vertex, and then rotating. Okay. So we translate one vertex to another, choose congruent corresponding angles, of course. Rotating brings congruent corresponding side together. And since angle, side, angle criteria allows for these steps, we begin here. So this is where we are. So if triangle A prime, B prime, C prime was over here, translating it over to A would create triangle A, B prime, double prime, C double prime. Rotating it so that B double prime lands on B, we would then get this triangle A, B, C triple prime. So that's why there's 3 prime marks. We've moved it 2 times. Translation, rotation, and now here's where it is, and then it will reflect across AB onto C. But it says in order to map triangle A prime, A, B, C prime, triple prime to triangle ABC, we apply a reflection R across this line AB. A reflection maps A onto itself. It maps B onto itself because they are on that line AB. However, we say that the reflection of C triple prime equals C with a star up here, or asterisk. Though we know that our reflection of C triple prime is now in the same half plane of line AB as C is, we cannot assume that C triple prime maps to C. It could land here, it could land over here, it could land up here. So we can't assume that. So to prove this theorem, we need to verify that C star is C. Okay. By hypothesis, we know that angle CAB, this one right here, is congruent to angle C triple prime AB. Recall that angle C triple prime AB is the result of the 2 rigid motions of angle C prime, A prime, B prime. So must have the same angle measure as that angle. Similarly, angle CBA C triple prime. Similarly, CBA is congruent to C triple prime BA. So they're saying this angle is congruent to this one. since angle CAB is congruent to the reflection of C triple prime AB is congruent to angle C asterisk AB, and C triple or C asterisk are in the same half plane of line AB, we conclude that ray AC and AC asterisk must actually be the same ray, because the point A and C star define the same ray as AC ray. The point C star must be a point somewhere on that ray AC. Using the second equality of angles, angle CBA is congruent to the reflection of angle C triple prime BA, which is congruent to C star BA. We can also conclude that ray BC and BC star must be the same ray. Therefore, the point C star must also be on ray BC. And since C star is on both AC ray and the ray BC, and the two rays only have one point in common, namely C, we conclude that C is equal to the location where C asterisk has to land. We've now used a series of rigid motions to map two triangles onto one another that meet the angle side angle criteria. So we have an angle, included side, and an angle. Notice how the side goes to the two angles that are congruent. Okay, page 3, side, 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 triangle congruence criteria, SSS. Given two triangles, triangle ABC and triangle A prime, B prime, C prime. If AB is equal to A prime, B prime, C prime side, AC equals A prime, C prime another side, and BC equals B prime, C prime a third side, then the triangles are congruent. Proof. Again, we do not need to start at the beginning of this proof, but assume there is a congruence that brings a pair of corresponding sides together, namely the longest side of each triangle. So AC came from A prime, B prime, C prime being translated so that C prime lands on C, and then rotated so that A prime or A double prime lands on A, and thus B prime is right here. So that's where we are. They're calling it B prime in this case, but it should actually be B triple prime. But anyhow, without any information about the angles of the triangles, we cannot perform a reflection as we have in the proofs for the SAS and the ASA. What can we do? First, we add construction. Draw an auxiliary line from B to B prime and label the angles created by the auxiliary line as R, S, T, and U. Since AB equals AB prime and CB equals CB prime, we know that they're congruent, there's marked. Then we know that triangle A, B, B prime, this triangle right here, the whole thing on this left side, and triangle C, B, B prime, this one over here, okay, are both isosceles triangles, congruent, congruent, respectively by definition. They have two sides congruent, they're isosceles. Therefore, R equals S, because they are base angles of an isosceles triangle, ABB prime. Similarly, the measure of angle T is congruent to the measure of angle U because they're base angles of the triangle BCB double or B prime. Okay, hence angle ABC, okay, equals the measure of R plus T. Okay, so let me draw this. So what they're saying is angle ABC, this whole thing, let me highlight it. So they're saying this angle here is equal to this angle plus this angle. Doesn't that make sense? Okay. So it is also saying ABC equals the measure of R plus T. But that's also equal to the measure of S plus U, because we've already said the base angles T and U are congruent because they're opposite sides. R and S are congruent because they're base angles in an isosceles triangle. So if R plus T equals ABC, then S plus U equals AB prime C. And R is equal to S and T is equal to U. So now we can say that R plus T is equal to S plus U, and that's right here. Which means that angle ABC is equal to angle AB prime C, because AB prime C is equal to S plus U. So therefore, by transitive, okay, if A equals B and B equals C, then A equals C, sort of. There's another equal sign in there, but anyhow. Since the measure of angle ABC equals the measure of AB prime C, we say that ABC is congruent to triangle AB prime C by side angle side. Okay, because we had this side, we had this side, and we have this angle. Triangle ABC is now this triangle up here. And triangle AB prime C is down here. So we already knew this side was equal to this side, and this side was equal to this side, and this side is equal to itself because of the reflexive property. But now we have an angle in between this side and this side. So it's an included angle here. So by side angle side, this triangle equals this big triangle up here. That's what that is saying. Okay, so we now have used a series of rigid motions in construction to map two triangles that meet the SSS criteria onto one another. Note that when using the side-side-side triangle congruence criteria as a reason in a proof, you need only state the congruence and SSS. Similarly, when using the angle-side-angle congruence criteria in a proof, you need only state the congruence and ASA. Now we have three triangle congruence criteria at our disposal: side angle, and side-side-side. We use these criteria to determine whether or not pairs of triangles are congruent. Okay, so page 4 finally brings us to an exercise. Now it's time for you to do some work. So pause the video, see if you can do these three, and then unpause the video and I will go over them with you. So here we go. Exercises based on the information provided. Determine whether a congruence exists between triangles, if a congruence exists between triangles, or if multiple congruence exists. Okay. State the congruence and the criteria used to determine them. So if a congruence exists, you need to state the congruence and criteria used. So here's a given. M is the midpoint of HP. So here's HP. M is the midpoint. Well, what does midpoint mean? It means that it cuts a segment into two congruent pieces. So now I know HM equals MP. That is a side. Okay, see how we do this? The measure of angle H, let's change colors. The measure of angle H is equal to the measure of angle P. There is an angle. I will call that an A. So here's a side, here's an angle. Don't know anything about HG or RP. Don't know anything about GM or MR. But don't forget that we know that angle AMG is congruent to angle PMR because they are vertical. So now we have another angle, and the side is in between. So we would say triangle GMH. It does not matter what you name the first triangle. It matters that the corresponding parts go in the right order when you name the second one. So if I started at G and went to M and then to A, which was my congruence, the angle that's congruent to the other triangle has to come last because my H is last. So what's congruent to H? P. So P's got to be last. M is my middle. That doesn't change. And then the other angle is R. So that would be GMA is congruent to RMP. Okay? Reason, angle, side, angle. Okay, number 2. Given rectangle J, K, L, M with diagonal KM. All right, rectangles by definition, opposite sides are congruent. So JM is congruent to KL. Likewise, JK is congruent to ML. Okay. All right. This has different answers. There's different reasons. If I'm stating this because of the reflexive property, I now have 3 sides. So now I can just say triangle JKM is congruent to triangle LMK. Careful how you name the second one. You can't say LKM. It's not lining up your congruent corresponding parts correctly. Okay, so the reason here is SSS. There are other reasons though. So I'm going to erase this. And now I'm going to state another reason. Well, if it is a rectangle, by definition, rectangles have 4 right angles. So I know J and L are right angles, they're congruent. Now I have a side, an included angle and a side. So that's where SAS comes in. Okay. And then similarly, we can say, well, if this line, let's erase this now, start over. Now I have a line here and a line here. LM is parallel to JK. And KM is a transversal. So therefore this angle here is congruent to this angle here because they're alternate interior angles. So angle LMK is congruent to angle JLM. Now I have one angle, and then if I use the same reasoning over here, these are also alternate interior angles between 2 transversals with KL and JM. So now I have angle, reflexive side, angle. So that's ASA. Let me just change colors here for that. Okay. So those are the 3 ways we can prove those 2 triangles are congruent. Okay, number 3, given RY equals RB, always label your diagram. RY equals RB. That side is equal to this side. AR is equal to XR. Okay. All right, so what else do we have? We have triangle ARY with 2 sides, and we have angle ARY congruent to angle XRB because they're vertical angles, and vertical angles are congruent. So now I can say triangle ARY is congruent to triangle XRB. Reason, side, angle, side. Okay, let me erase those, leave the givens. The other way we could do it is we can look at the entire triangle here, ABY. Okay, that wasn't very good. Anyway, you get the idea. ABY is this big triangle, because if this piece is congruent to this piece and this piece is congruent to this piece, then AR, which is this length, and RB, which is this length, is going to equal XR plus RY. So AB length is equal to the XY length. We then have YB congruent to itself, and this triangle here and this triangle here share this side by the reflexive property. So now I have this side and this side. Okay, so now all I need is an angle. So what am I going to do about that angle? Let's see. Okay, so now this one's a little tricky. So what we do is, if we focus on this triangle right here, that is an isosceles triangle because these two sides, see those two sides are congruent? Well, if those two sides are congruent, then that just states the fact that this base angle is equal to this base angle, okay? So now let me get rid of these red lines. So now I have this side here congruent to this side here, that's a side. I have this angle, base angle down here congruent to this base angle down here, that's an angle. And then I have this side congruent to itself by the reflexive property, so that is SAS as well. But what triangle is that? That is triangle ABY. A is congruent to X, so A was first, so X has to be first. B is down here, that's congruent to this angle here, so XY. And then B is so. So triangle ABY is congruent to triangle XYB by side angle side as well. Okay. Okay. Page 5 brings us to problem number 4 and 5. Again, there's our exercises. So pause the video, see if you can do them on your own. And if not, or even if so, come back and check your answer. So here we go. What I've done here is I've taken these triangles and I've drawn them up. I've copied them into different colors. So that way I can move them like so. So I just moved, this A was right here, this B was right here, and the C was down here. So that's triangle ABC. And then if I move this blue one over here, the blue one was D, C, B. Okay. Keep in mind that BC is congruent to itself, so I do know that. We were given the measure of angle A is congruent to the measure of angle D, so I'll label these in both diagrams. And we were told that AE was congruent to DE. Okay, AE is not in this because that's the intersection of these two sides, so E is somewhere around here and E is somewhere around here. Okay, so I'm not going to do anything with that right now. But for starters, I have an angle, I have a side, and the easiest way to do this one is, these are vertical angles, they're congruent. So now I have angle A congruent to D, AE congruent to DE, that's an angle, that's a side, and now I have vertical angles are congruent, so I have two triangles with ASA, and that is triangle ABE is congruent to triangle DEC. And the reason is angle, side, angle. Okay, so now that I know that, since this triangle is congruent to this triangle, then the corresponding parts of congruent triangles are congruent. So now I can say that BE is congruent to EC. So if BE is congruent to EC and ED is congruent to EA, then the sum of their parts is equal to the whole. AC equals DB. AC equals DB. So now I have an angle, I have a side, I have a side. There is no SSA theorem, so I need to do something else. Oh yeah, right here. I already did that. I have the sides. Reflexive. Okay, so what else do we have? We have, let's take a look. AB, since this triangle here has side AB congruent to side DC, by corresponding parts of congruent triangles being congruent, now I can say AB is congruent to DC. But you would have to do that triangle first to get these pieces. So now I can say triangle ABC is congruent to triangle DCB. And the reason here is we could do this side with this angle and this side, that'd be SAS. And we could do side, side, side with all three sides. Okay, and there are others, but those are just two. All right, number 5. Let me erase this so it's not distracting. Number 5 says that AB equals AC. So the first thing I'm going to do is label my diagram. This whole side here is equal to this whole side over here. Okay. BD is a quarter of AB. So this is 1/4. So this would be 3/4. So therefore AE is 3/4. 3/3 is 1. 3/4, 3 out of 4. And EC or CE is a quarter of AC. Well, if the whole thing is congruent to the whole thing and I cut quarters off of each, those quarters are going to be congruent and the pieces are going to be congruent. So AD is going to be congruent to AE, DB is going to be congruent to EC. So now I have that all labeled up. Okay. So now I have side AB congruent to side AC. We knew that. But I also have, let me do a different color because it's hard to visualize if I don't. Let's see, if we're looking at this triangle here, let me copy this down. So I move that out of the way. Let me label its vertices. This was A, this was B, and this is E. And I know that this is congruent to, that's AB. Now I'm going to do another triangle. Let's do this one in blue. So I did ABE, now I'm going to do ACD. Okay, so copy those, make them group together. Group, group, move, and label their vertices. This was A, this is C, this is D. So I know AB is congruent to AC because it's a quarter of AB. Well, AB is congruent to AC. That was the given right here. So that's what we know so far. Okay. Okay, now look at AE. AE is 3/4 of AB. Since CE is a quarter of AC, then AE is 3/4. So if AE is 3/4 and AD is 3/4 of the two equal pieces, then AD is going to be congruent to AE because it's 3/4 of a congruent piece each, if that makes sense. So now I have a side over here, a side over here. All I need now is an angle A. Oh, reflexive angle, there it is. Okay, so now I can say triangle ABE is congruent to triangle ACD by side angle side. Okay, that one was a little tricky. You just had to use the proportional sides to finish and remember that angle A was shared in both, so they're congruent. Okay, page 6 brings us to the end of lesson 24. Go do your problem set.